First of all, thanks for giving me the opportunity to speak about geometry of a function field. And I would like to start with remarking something that perhaps everybody knows, that there exists an analogy of the arithmetic of a z and arithmetic of a c of t. And actually, in the third lecture, we will speak also about f q bar of t. And these rings are all, they look similar. They are all Dedekind domains. And you also have, so they are Dedekind domains. And I will not write it down, but you also have a very interesting feature, which is a product formula. Which is, if you take M, if you call F one of the field of fraction of one of these three rings, and MF is the set of absolute values. I've duly normalized. You have that for every A in F star, the product of a view of MF of A view is equal to 1. And you also can remark that the arithmetic of extension of these rings are very similar, and in some way you can imagine this as the relative dimension 0 varieties over these rings have very similar theories. So you will be interested to study variety of higher dimension. So you take F, again one of these fields, and you consider XF a smooth projective variety over F, and you would like to understand the arithmetic of it. You would like to understand the arithmetic of it, and you have two main meta questions. Meta question 1 is can you understand the structure of XF of F bar? These are the set of algebraic points from the geometry of XF tensor F bar. So this is a purely geometric object, and you would like to understand the arithmetic of it. And of course, this is a vague question, and as you see, I'm not specifying the field I'm working on, just keeping this. And the second meta question question 2 is can you find a general theory which allows to study meta question 1 without specifying in which case f is. What I mean is you have a general theory which works, a general language if you want, and just at the end of your research you decide which of the three fields you are, and then you interpret it in terms of the situation. Both are very interesting, and today I will focus on this second question. And unfortunately, I will focus on this, and I will try to show some particular feature in the function field case. This will be is a little bit more delicate. I will speak about it in the third lecture, but I will focus on this part. And what is? But before, I will recall something on the number field case. What I would like to speak about in the meta question 2 is height theory. And height theory, and I will recall it the basic facts of height theory in the number field case. So in number field case, and I write it here because we will keep it here. So we consider x, so f now in this blackboard is a number field, and xf projective variety, and I will denote by f. This is not f xf f bar r is the set of function from x f of f bar to r, any kind of function, Kanti set theoretical function, and b of x f f bar r are bounded function, and f u b is f x f f bar are divided by b of x f f bar r. So these are function up to bounded function, and an element here usually is denoted by a class here is denoted by h plus o of 1. And I hope that you know that there exists a height machine which says that there exists a group morphism height from peak of xf to fu b to L we associate HL, which is even unique, which with the following properties. First is functoriality, if G from xf to yf is a morphism, we have that H G apple star of L of P is equal to H L of G of P. And I will write plus O of 1. It says that they are in the same class. And second property is of Pn is what you know over if xf is equal to Pn and L is equal to O of 1, the tautological bundle, you have that H O of 1 of P is defined in the following way: is the class of this. You take P x0 xn and then H O of 1 of P is equal to 1 over F over Q sum so V in MF log max. Okay. Here there are only 2 balls. Okay. And I would like to recall the following 2 important properties. First property is if D is a divisor inside XF and P is not in D, H of D of P is lower bounded, and this is independent on P. So there is a uniform lower bound for points which are not inside a divisor. And second very important property is Northcott property. If L is ample, and HL is a height, so I mean a representative of the height, A and B constant, the set of point P in XF of F bar such that F of P F is less or equal than A and HL of P is less or equal than B, this set is finite. So this is essentially the height theory for in the number field case, and essentially this gives you the definition because every line bundle is difference of 2 ample line bundle, and these are the very important features that are usually used in arithmetic. So what I would like to discuss is a similar theory in the function field case. And why I would like to speak about this is because it's the, to my knowledge, is essentially the only one of the few cases where the function field case is more complicated than the number field case. Something very, well, we will see what happens in the function field case. So we would like to develop a height theory for varieties defined over extension of C of t. C of t, which from now on this will be f. Before it was before a number field, now it is a function field. An extension f of I do not use the letter k because k is the canonical line bundle. What is the situation? I have xf defined over spec f, and what is important is that f is the function field of a smooth projective curve. And for every, let's say, what letter I use? For every f1 extension of f, I have that f1 is C of B1, which is another smooth projective curve, and I have a morphism alpha from B1 to B, which is a finite cover. Okay, and this is for notation. And now I will introduce the concept of models. So a model of xf is a projective variety x for which with a morphism x over b, for which the following diagram is commutative, is Cartesian, sorry. And I will suppose that with a flat morphism. So I don't want to add the components which are useless. And I can also say a model for a line bundle L over xf is a line bundle L over x such that E upper star of L is equal to L. Now, a point, F1 point of xf is a morphism from spec of F1 to xf. And there is a criterion called the valuative criterion of properness, tells us that there exists a bijection between point P of xf of f1 and morphism capital P from B1 to X like this. And I see very well what is given a point here. I just remove, it just comes from I upper star of P. The generic fiber of a point gives us the generic fiber of a curve gives us a point here. The criterion says that this is a bijection. So each time you have a point here, you can extend it to the morphism to a curve. Okay? And so I want to define a height theory. So I want to tell you when you have a point and a line bundle, what is the height of this point with respect to the line bundle. So I will define a function height from peak of xf to fu b xf or q in this case. So this is function up to bounded function, which to a line bundle L gives a function HL, and HL I have to tell you what is the value on a point, and HL of P is just 1 over F1 divided by F, the degree of capital P upper star of L. Of course, the class. And okay, this may seem to be a strange definition with respect to this, but I will not insist too much on that. But if you work in hierarchical of theory, you will see that this definition is exactly this definition using the correct translation. Okay. And now what you see is essentially by construction that, okay, remarks. If xf is equal to P1, to Pn, a point P in xf of F1 is a morphism from B1 to Pn, defined over C, and HL of P is just 1 over F1 over F, degree of capital P O of 1. So morally, you have to think that up to this normalization, the height is the degree of the curve of the image. Morally speaking, you take the image is a curve, you compute this degree as a curve in Pn, and this is the height. And And you see that property 1, which is here, is essentially true by construction. And now we come to property 2. And property 2 is much more delicate. So you expect, you would like that height theory verify this property, but actually the situation is much more complicated and actually is even false. Let's study property 2. Suppose that suppose that x0 is a variety defined over C. Then we can look to x0 tensor F. This is a variety defined over F. It's just a variety with equations which do not depend on the parameter t. But you see that x0 of C is contained in xf of F. And a model of xf is x0 times b over b. So here is exactly the situation. If you take P to be a point in x0 of C, you can see from here that the height of P is just the degree and 1 over F, okay. The degree of P upper star of L, but L is, P upper star of L. But that section, but this point this point P correspond to the section P times B. So this height is 0. What this means that all the points which are defined over C, in this case, have bounded height. And so you cannot hope about a Northcott property for this kind of variety. And for this reason, you introduce a class of variety, which is essentially this class, but is a little bit more general, which is the class of isotrivial variety. You will see that isotrivial variety will play important role in the function field case. So, definition: a variety xf is said to be isotrivial if there exists a variety x0 defined over C such that x0 times C f bar is isomorphic to xf times f bar. What I mean is that the variety becomes isomorphic to something defined over C, but over the algebraic closure. And just to give you an example, you take x to the power n plus y to the power n plus t, z to the power n equal to 0 in P2, and f c of t, this variety is isotrivial, but is not defined over C. So this variety you cannot define this variety over C, but if you add the n root of t, this variety becomes isomorphic to a variety defined over C. And so this is an example of isotrivial variety, and you will see exactly by generalizing the example I gave before that this curve has infinitely many points defined of an extension of C of t, which have a bounded height, which have bounded height equal to 0, because just add the root of t, and then you are exactly in the situation as before. So you take all the points defined over C, and then you project over this curve, and you have many points. So isotrivial varieties cannot verify a Northcott theorem. Isotrivial varieties are a feature which exists, as far as I know, only in the function field case. I don't know a good definition of isotriviality in the number field case. And they are so important that I would like to list some properties, facts about isotrivial variety. Today we will not see too much, but we will see in the future, in the lecture after, that you have really to be careful about isotrivial variety. First fact is that X is isotrivial, xf is isotrivial, is equivalent to say that for every model xu over x over b, there exists there is an open set U in B such that for every t in U, xt is isomorphic to a fixed variety defined over C. You see, xt is just p minus 1 of t. So that means, isotriviality means that the variety do not deform. Actually, it's just a constant family as a geometry. Second, second thing which is true, this is second fact, which I will use it tomorrow, which is for characteristic 0. So it means that I am working over C of t and not over fq bar of t, is that if there exists is isotrivial projective variety ZF which dominates XF, dominant, which ZF with a surjective morphism ZF over XF, then XF is isotrivial. So to be dominated by something isotrivial implies isotriviality. This is false and characteristic P. So these are something which says you something what isotriviality means. Isotriviality means do not deform. And one important thing which is isotriviality is not a birational property. This is something which should scare a little bit, because often many of the conjecture you know in the function about structure of algebraic points are conjecture which are birational, which if you take a variety or a birational model of it, they are true. But you see that if a variety is isotrivial, you have many rational points. They are Zariski dense, they have bounded height, so you cannot hope any kind of Lang conjecture in this case. So you are tempted to say, okay, I will just say, take a non-isotrivial variety and I will state my conjectures. And the thing is, no, it's not enough, because you can have that your variety is not isotrivial, but it has a birational model which is isotrivial, and so you will construct all the rational points you want. Just to take an example, okay, I'm quite late, is that if you take, for instance, P2, and you blow up P2 in 9 points very general, this can, and these points move, this is something which is not isotrivial, and which is birational to P2. And even if you take, even you can say even more. You take, you can take, for instance, a variety of general type, defined over C. You blow up it in points which are defined over F, which are very general, many points, and you will find a variety which is of general type, which is non-isotrivial, but with Zariski dense points, because all the points coming from the open set are, from the open set where you didn't do anything, are rational points. So isotrivial varieties are very delicate in this situation. And okay, I will state at least one theorem which says something about the relation of isotriviality with Northcott's theorem. And so it takes 5 minutes. And then tomorrow I will say more about this. So the theorem I want to say is the example of points of bounded height which are coming from C is essentially the only example I can imagine. The theorem is this. Let's say theorem. You take XF variety projective variety. Smooth. L ample line bundle. And you also fix a representative of HL, and you fix a constant A, and then you consider SA to be the set of point P on XF of F, such that the HL of P is less or equal than A. So I am looking to the point of bounded height, rational point of bounded height, and the theorem is then there exists a quasi-projective variety U defined over C, and a set of point S, set of points of U of C, and a map from U and a map like this, such that C of S contains S. So what I am saying, SA, sorry. So the situation is saying that if you have a set of points of bounded height, morally speaking, you can imagine that they are coming from a variety which is defined over C. Be careful, because this variety is quasi-projective, not projective. So this is why I say this, because you can say, okay, let's suppose that the set of rational points of bounded height is Zariski dense, that I am proving that there exists a map from this to this which is dominant because it contains a Zariski dense point, and this is isotrivial, and I would like to use this property to deduce that this is isotrivial. But actually the answer is not, because here I am supposing that it's projective. But okay, I am late. Tomorrow I will say how we can strengthen this property to obtain some kind of useful Northcott type theorem, which will be useful to study arithmetic of algebraic point. Just to mention, if in the Northcott theorem you also take point of defined over a finite extension, this is absolutely false. There is no statement in the function field case. I can construct curves which are not isotrivial with infinitely many points of bounded height which are defined over fields of degree fixed, degree at most 5. So the stronger version of Northcott theorem is false. What I will hope is to refine this theorem to find something which will be useful to study rational point. But it is late, so I will continue tomorrow.